Okay, good morning, physics students, or good afternoon, or good evening, depending on when you're seeing this. Hopefully you guys are doing well. Wanted to give you a quick little lesson on work that'll help you with today, Monday, March 23rd. I think Monday, March 23rd's work, and that literally is what we're talking about today. It's work. I'm gonna try sharing my screen with you here, and let's see if we can make some stuff a little bit more clear about some of the stuff we were doing last week and add in a little wrinkle here. So what I'm going to propose to you is that we consider the following situation. We're going to have a little bit of a hill, and let's say that that hill is 5 meters tall, and we're going to put at the top of this little thing a 100-kilogram sledder, and we're going to say that the sledder is at rest. All right, and then we're going to say, all right, so we're going to go down the 5-meter hill, and we know that we could figure out the velocity at the end of the hill using this conservation of energy stuff that we were dealing with last week. I'm going to make that a little bit bigger for you guys at home here. So we could totally work with conservation of energy here. We remember that the total initial energy equals the total final energy, and so we would have potential at the beginning, and we would have kinetic at the end, potential at the beginning because all we have is height and no motion, and kinetic at the end because we no longer have height, but we do have motion. And so at this point, we go in and we go ahead and solve it. We'd say that 100 times 9.8 times 5 is equal to 1/2 times 100 times v squared. And if we get out our calculator and did some math, we'd figure out what that velocity is. I don't have my calculator handy, but I trust that's math you can do. Now, how would this problem change if we took the problem and we only did it partway down the hill? Well, we're still going to have the law of conservation of energy taking place, but in this case, we'd have to realize that we'd be looking at a situation where our initial potential energy is converting into not only kinetic at the end, but it's still going to have some potential here. So we'd have UGI equals UGF. So the initial potential is equal to the potential at the end, the final potential, plus the kinetic. I'm going to not put all the numbers in there, but some of you expressed a little bit of difficulty deciding what type of energies go where, and they're basically two questions. You ask yourself, does it have a height? And if it has a height, you know that it has potential energy. And you ask yourself, does it have motion? Does it have velocity? If it has motion, then you know it has kinetic energy. So hopefully that clears some things up. But now we're going to throw a little wrinkle into the mix, because the reality is this. This works really great if it's frictionless. But what if there's some friction? If there is friction, do you think that the amount of energy at the beginning would still be equal to the amount of energy at the end, or would friction be putting energy in or taking energy out? And I think we know that the answer would be that friction would be taking energy out. So what we want to do is we want to consider a situation where maybe we have the exact same ramp and the exact same block, but now we talk about maybe a little bit of energy gain and or energy loss. And so physicists call this energy gain and or energy loss, right? They call this work. All right. So if I were in your shoes, I'd be sitting there writing down that work is just an energy gain or an energy loss. And so what we can do is we can say, all right, if we still have, sorry about putting my hands over stuff there, my 100-kilogram box sitting on top of a 5-meter ramp. And let's say that by the time that this 100-kilogram box gets to the bottom, it is going 1 meter per second. Now we know from our work from the other problem where it was frictionless, we could have found the velocity that it should have had here without friction. But now what we get is a more complete statement of our conservation of energy, right? total initial energy is still equal to total final energy. But what we have to add in here is this work term. And you'll notice that I'm going to always put a plus W. And the reason for that is that the signs will work out. And you'll see what I mean as we go through this here. So let's go in here and just kind of do the actual math for this. And this might be a little bit tricky for me. I've got too many applications running, and I don't know that I have a calculator immediately easily available. So let's go ahead. We know that we have potential energy at the top. We know that we're going to have some energy loss due to some friction. And we know that that's going to convert into kinetic energy at the end. And so at this point, we go ahead and say MGH 100 times 9.8 times 5 plus work. And we don't know what the work is. We don't know how much energy is gained or lost here, but we just leave it as plus work. And then we think about, okay, kinetic energy is 1/2 times 100 times 1 squared. So I'm going to do the 100 times 9.8 times 5. That's 500 times 9.8. Sorry for all the clicking here. That's 4,900. And energy, remember, is in joules. And that's work. Half of 100 is 50. 50 times 1 is 50. And so if I do this math, I'm getting 50 joules minus 4,900 joules. And it's beautiful because here I'm getting a negative sign. And I wonder why that might make sense. Oh yeah, it's friction. Friction isn't going to put energy into the system. This is representing an energy loss for the system. So from the perspective of the block started out with 4,900 joules worth of energy, right? I can scoot that up. Didn't realize I was off screen there. 4,900 joules of energy to start with. It only had 50 joules of energy at the end of the hill, at the bottom of the hill. Well, what happened to it all? Well, it turned into thermal energy. And we've seen this before. When we talk about things rubbing up against one another, things get hot. And so that energy goes literally out into the universe as heat. So the idea of work is literally just think about what type or types of energy you have at the beginning, what type or types of energy you have at the end, and we just put this little W term in there. Let's look at another example real quick. So the second example here, think about a rocket sitting on the ground. So here's my beautiful rocket. It's got no height and it's got no velocity, so it has exactly no energy. Well, that's boring, all right? So we light that sucker up, and now at some time later on, rocket is up here. Sorry for the sound effect, and can't help it, it's a rocket. Let's say that 10 meters up, this thing is now going 5 meters per second. So clearly this would be a situation where you had no energy to begin with, and now you have definitely the total energy at the end. You've got some kinetic because of your motion, and you've got potential because of your height. So these can't be equal to each other, right? What we were doing last week, total energy at the beginning equals total energy at the end, that's complete bumpkus. So what we have to do is we have to add in the more realistic idea of work. Work is energy gain or energy loss. So we could determine how much work was done in this situation, all right, by literally coming in here and saying, look, we know that we have no energy at the beginning, all right? Something to consider, what is doing the work? What is giving the rocket the energy? Well, without the rocket engine and the fuel, this thing wouldn't gain height and gain velocity. So that's where the energy change is coming in. The work is being done by the rocket engine. And so that's going to be equal to the kinetic energy at the end plus the potential energy at the end. And so then we're off to the races. We know that the work done is equal to 1/2, and I don't know the mass of the rocket. So let's do one of these with M in it. So I've got an M times 5 squared, and then I've got an m times g times h. So half of 25, that's going to be 12 and a half, 12.5 m joules. And notice it's just got an m. This is going to be 98 m joules. And so 98, 108, I'm going to guess that that's 110.5 m joules. So the amount of energy that the rocket put in, excuse me, the engines put into the rocket would be 110.5. So listen, that gives you a quick sort of run through of how to do work. Those were two problems where you were having to find the work. If I gave you a problem where I gave you some other information and I said, how fast or slow is it going later on? I think I'd like to do one more example with you there, and that should get you pretty much set up for doing the problems that I've asked you to do in the problem set for today. So let's go ahead and go back to a ball being thrown. And excuse me, I'm going to cough here. I'm going to try and mute the speaker before I cough. I don't know if I'm going to get it. Sorry about that. All right, let's go ahead and start with a ball on the ground being thrown upward at 20 meters per second, and it's on the ground. And let's say that air resistance is going to take some energy out. It removes 100 joules of energy. So if I'm removing energy, you should think about whether that's going to be a positive or a negative quantity. I don't think that's going to be too hard for you to figure out. But if I'm removing energy, I'm probably having less at the end. And let's go ahead and say that the object is at some later point, it's now at a height of 5 meters. And I want to know what's its velocity. All right, so off to the races. We say, look, total initial energy. Now we add in this plus work term equals total final energy. And some of you are like, well, wait a second, Mr. Caldwell, why are you adding work? It's an energy loss. Well, I'm going to take care of that loss in just a second, so don't you worry. So I go back and I say it's on the ground. It has velocity, so it only has kinetic energy. That kinetic energy is going to have a little bit of an energy change to it, so we put work in there. And then we say, what type or types of energy does it have up here? If it's 5 meters up and we think that it's moving, well, it's got potential and kinetic. And we're almost wrapped up here, guys. So let's go ahead and finish this off. Now, this one, I didn't give you M, so I'm going to go ahead and do it without the mass because I want to show you something. All right, so I've got plus W. And really, I can go ahead and put in that this is, and this is the way I prefer to do it. I always put plus, and then I remember that I'm removing 100 joules, so I'm going to put plus a negative 100 joules. Now, if you're like, Mr. Caldwell, I know that's a minus sign, go ahead and do that. That's okay. But I just always like to keep that plus sign because this shows me, hey, this is a loss. And then I'm going to go ahead and M times G times H, height of 5 meters, because I'm doing potential energy, plus 1/2, and I'm getting a little bit towards the edge of my screen there, so let me go ahead and do 1/2 m times v squared. Now here's where you have to really be careful, all right? I've got an m here, an m here, an m here, and you're like, ooh, let's cancel them out, but where I don't have an m is right here, all right? So that is going to make this a little bit uglier math-wise, all right? So don't go canceling m's unless you have an m in every single term. So since this math gets pretty ugly here, I want to go ahead and make the math not ugly. Let me make the mass 10 kilograms, all right? Because if you did this math, you could totally solve for v, all right? But you'd have an awkward and ugly answer, and I don't want that. All right, so let's go ahead and do 1/2 times 10, and I'm a little bit too low there, sorry about that. 1/2 times 10 times 20 squared minus 100 equals 9.8 times 5, which is 40. I want to say that's 49 times 10. That would be 490 plus 1/2 times 10, which would be 5. And I'm going to leave that algebra to you because I think that you guys should be pretty good to go at this point. So that's my hope. Hopefully this gives you a little bit of a better insight into how we would go about figuring out work problems. So I think I've stopped sharing there. Hopefully you guys have a great day and that this wasn't too terribly long for you and that the helpfulness was going to outweigh the length of the video. You guys have a great day and I'll see you soon. All right, bye-bye.